Alright, in a previous video we looked at the definition of the cross product, and assuming that we knew some vectors, v and w, we made this kind of long, cumbersome definition for something called the cross product. And the important idea there is that the cross product of two vectors is a new vector that is perpendicular to both the given vectors v and w. So essentially, the dot product of v and w with the cross product, both of those equations come out to equal 0. So we had this definition of the cross product, and the computer itself over here on the right. I mean, it's pretty straightforward to ask the computer to cross product the vectors v and w, and you will find that you get the same equation that we have over there on the right hand side of the screen. Okay. So one thing we need to just talk about is just to make sure everybody can compute like the easy way of by computing the cross product by hand. Okay, so I want to look at that right now. Let me see, let me switch this one to orange. So if we're going to compute, for example, the vector v crossed with w, okay, the way to do that is to compute a determinant, okay, of the following the following objects. So we have the vector, sorry, I, j, and k up here, and then you write your vector v1, v2, v3 on the second row, then write your vector w on the third row, the entries of the vector w relative to the ijk coordinate system. So writing the vectors v and w in the standard coordinate system. And then according to the cross product, we know that we are going to get an answer that is something times the vector I plus something times the vector j, and then there is a third entry plus something times the vector k. And the easy way to figure out what goes here is a determinant of a smaller matrix. So here, the notation, the vertical bars around this block of numbers is called a determinant. This is the determinant symbol. All right, and what we need to do is in the I entry, we need to look at a smaller set of blocks, V2, V3, W2, W3, and to take the determinant, we need to take the determinant of the matrix V2, V3, W2, W3, which a determinant is done by multiplying the numbers on the diagonal, right, of the 2 by 2 matrix, and then subtracting the numbers on the off diagonal V3, W2. And you can see that that's the formula that we got up here. Okay. So when you get to the J entry, it's also a determinant expansion, but there's an artificial minus sign in the problem, and then we will use the numbers to find the determinant V1, V3, W1, W3, which gets computed to V1, W3 minus V3, W1. Okay, and then there is the artificial minus sign on there. Okay, the K entry, we're going to focus on V1, V2, W1, W2, V1, V2, W1, W2, and the determinant of that small block is V1, W2 minus V2, W1. So, the linear algebraists have determined that these determinants are important, and we can see that they show up in an odd place when it comes to computing the cross product of a vector. We have three little determinants to compute to help us figure out the numbers that go in the I, the j, and the k entry of the cross product vector. All right, so hopefully that'll give you a little bit of a idea of how to compute these vectors by hand. And we can see over here, we got it. Let's go ahead and look just at a specific example, of computing this just before we start looking at properties of the cross product and what the cross product is actually doing. definitely it's probably good to compute an example, right? Or at least another example. More examples, the better, I suppose. So here we have a vector A and B, and our goal is to compute the cross product of those vectors. Now, according to what we've learned in class, we need to compute a determinant, but a determinant of what? A determinant of ij and k along the top, 1, 0, 4, negative 2, 1, 3. Okay, so as we did before, we are going to select the I entry and figure out a number that goes in front of that, which is going to be the determinant of 0, 4, 1, 3. Okay, then we're going to move to the j entry plus the j entry, and then we will have another determinant with an artificial minus sign of 1, 4, negative 2, 3. And then finally there is the last entry, the k entry. Okay, and then we will have, the determinant of the 1, 0, negative 2, 1 submatrix. So for those of you who are in linear algebra, we're essentially kind of doing what is called the cofactor expansion of the determinant. Okay, and it's just up to us to finish all the different numbers. So the I entry will have 0, 3, which is 0, 4 minus 4 times 1 is 4 with a minus sign because of the determinant. We will have an artificial minus sign on the j, 3 minus a negative 8, and then the k entry will be plus 1 multiplied by k. Alright, so negative 4i is negative 4, 0, 0. 3 minus minus 8 is 11, so that would be, and distribute the negative through, so lots of minus signs to worry about there. Plus 0, negative 11, 0, and then the k clearly comes out to be 0, 0, 1. So if I'm putting all this together, I can say that A cross B is equal to the vector negative 4, negative 11, 1. I guess the final decider on whether or not we did that right, I'm going to take the cross product of the vector A with B and hope that Alright, didn't quite get that right. Do I have the same vectors here? Negative 2, 1, 3, 1, 0, 4, negative 2, 1, 3. Okay, let me double check my expansions. I got 0, 4, 1, 3. That's good. 1, 4, negative 2, 3. I like that. And then the k, 1, 1, 0, negative 2. Okay. So the I get negative 4. I think we're agreed on that one. 3 minus a minus 8 is 11. Cross producting A with B. Alright, let me pause for a second and I will see if I can find my mistake. We're back. Everything was done correctly by paper, but for some reason the vectors A and B in the computer's memory must have been off. So we can see here that A cross B, when I reevaluate this, turns out to negative 4 and negative 11, 1. So the answers that we expected to get from our hand computations. Alright, so the next thing we need to talk about is geometric interpretations. Geometric interpretations of the cross product. Like why are we working so hard on this computation of the cross product? Now the easy answer here is that remembering from the definition, right? So if you have V and W given, you can find V cross W, right? That maybe the way to see this is just to remember that the cross product was defined in the first place, right, as was supposed to give us a vector perpendicular to the vectors V and W. So just to make this a little bit easier to see, I'm going to kind of complete the edges. I'm going to kind of make copies of the vectors v and w at the ends of the vector v and w, and we can see here that that we have this kind of plane defined. So the way I'd like you to think of the vector v and the vector w is think of them as the edges of the shown parallelogram. Right? And so when we're looking at v cross w, there is a third vector that we could be drawing on this picture, and this third vector is perpendicular to both v and w, right? So the cross product here, we could say that v cross w is a vector perpendicular to the plane or the parallelogram whose edges are the vectors v and w. Okay, so that might be the first geometric interpretation of the cross product, just following directly from the definition of the cross product. There's another important idea here, and it kind of builds off exactly, I'm just going to kind of sketch them here again, builds off of this idea of the parallelogram. Okay, so here we can see that there is this parallelogram defined by the vectors v and w. Right, and the cross product has something to say about the geometry here, that if you were to compute the magnitude of the vector v cross w. Now remember, we know how to compute a length or a magnitude of a vector. We need to take that vector and dot product it with itself, and then take the square root. So here is the length of the vector v cross w. Okay. Now, if you were to get that number, it also has an alternate interpretation, that it can be instead of the length of the cross product. So here's the cross product vector itself. If you want to find the length of that vector, it also happens to be the same number that would give you the area of the region of that parallelogram, where v and w are the edges of it. So we can also say that this is the area of the parallelogram defined by the vectors v and w. Okay, and if you'd like to see just a quick example of that, right, let's take just the simplest possible case. Let's take the vector v to be 3, 0, 0, and the vector w to be the vector 0, 4, 0. And if you were to compute the cross product of these two vectors, right, doing the methods that we are familiar with, right, you would compute the cross product, and we could see that there's only going to be one entry here. It's going to be the k, one non-zero entry. It's going to be the k vector with 3, 0, 0, 4 for the determinant we need to compute, which is equal to 12k, otherwise known as 0, 0, 12. So from there, if you were to compute the length of the cross product, right, you will get the square root of 0, 0, 12 dotted with 0, 0, 12, which is the square root of 144, otherwise known as 12, otherwise known as 3 times 4. So what we're saying here is that there's this interesting formula that the length of the vector v cross w is the length of the vector v, length of the vector w, and then unlike the cross dot product, there is the sine of the angle between those vectors. And what we can see here is that since the vectors v and w dot product to 0, this means that the angle between those vectors is 90 degrees, right? And therefore the sine of 90 degrees is equal to 1. So what we are finding here is that the length of the cross product is the length of the vector v, length of the vector w, which is 3 and then 4, but the sine of the angle between them is 1, and that 12 is where we're getting the area. Okay, so V cross W, the magnitude of it, right, gives you the area of that parallelogram. Okay, very important computation we just did there. There's a follow-on from the one-dimensional higher. So notice that we have two vectors that we are, in a sense, quote, multiplying. Here we are multiplying two vectors. And so here we can imagine the units to be coming out in terms of meters squared. When you're taking two things multiplied by each other, you might expect to have the units of meters squared, which is an area unit. If you bring in a third vector, there's an interesting computation that we can do and another interpretation of the cross product, but it also happens to bring in the dot product as well. So let's say that you have, let's say the vectors A, and you have the vector V, and then you have the vector W. Okay, so let's say that I may get rid of these computations here. Let me say that A is just some general vector, A1, A2, A3. Okay. And we know that we can compute the cross product separately of V and W, and then because the cross product is a vector, it does make sense from a mathematical standpoint that we can take the dot product of those vectors to get a number. Okay. So this answer might possibly come out negative. So if you put an absolute value on this number, we'll see what this positive number means in terms of geometric significance. Okay, so before we get too far into that, notice that we can do A dotted with the cross product of V with W. And we will get this rather long, complicated. Well, I thought it was going to be longer than that, but oh, shoot. Let me see. A, it's remembering A from earlier. So let me call this the vector F, A, B, C, D. We'll call this Z. Sorry, Z. I don't want to take the moment to clear the computer's memory. Actually, let me just show you how to do that, because that might actually come in handy. If you go to evaluation, quit kernel local, and you say quit, then you should, and then you can go back and rerun this, and the computer's memory should be cleared. That's the easy way to do that. And here is now this long dot product of A dotted with V cross W. So we can see that the answer is going to be some form of number, okay? And we will see that this will be equal to the determinant of the vector A with the vector V with the vector W, okay? So there is this interesting formula. This is called the left-hand side of that formula equation I've just written down. There is a right-hand side of that equation, which is the vector A, V, and W. Okay. Now look, A, V, and W, if I look at that as a matrix, right, is A on one row, V, and W. Okay, so when we say the determinant of A, V, and W, we mean to compute A1, A2, A3, V1, V2, V3, and W1, W2, W3. So we need to compute the vertical bars, the determinant of that thing. Now there is a cofactor expansion to that. So you would take A1, right, and then multiply by the box of numbers that doesn't involve the row and column that have A1. So you'd have V2, V3, W2, W3. Then you expand to the A2. You can go across any row or column. You'll learn that in linear algebra. But we would do V1, V3, W1, W3. And then there is a third column. I guess we'll just leave that in black, I guess. A3 plus A3 times V1, V2, W1, W2. And if you expand that, that's where you can see that we are going to get the determinant of this matrix. Mathematica likes to compute determinants, right? And we get this rather complicated looking answer, which is exactly the same as simplifying the left-hand side to the right-hand side. So if these are the same, we should get 0, the number, as our answer. So those equations are the same. Okay. So here we have, instead of, if you're in linear algebra, you know how to compute determinants, but if you're in Calc 3, we know how to compute cross products and dot products. And so what we're finding is that these answers are exactly the same. Now the geometric significance of this, when you compute like an absolute value, maybe I should put that just to make sure their answer always comes out positive. Let's say that you have the vector A, right? I'll draw A this way, and then maybe I had V and W, right? Which made this parallelogram, right? But now there's a third vector A, which kind of acts as a third dimension for this thing. And if I move the vector A to all the other corners, right, we will make A, try to make this thing look. What we're getting is some sort of what is called a wonky box, is what I would call it, or you can call it a parallelogram, right? And the question is, what is the volume of that box? Okay, the volume is given by a dot producted with V cross W, otherwise known as the determinant of the vector A, V, and W, the determinant of that 3x3 matrix. So these dot products and cross product operations are important for computing area and volume of fixed vectors in the following ways that I have done. So just a simple example, just so you can kind of see that everything's kind of working out together. Let's say you have the vector A, and I think you're going to see why I'm choosing this the way I'm doing it. Let's say that you get 1, 0, 0, and let's say you got a vector W is 0, 2, 0, right? So if I compute A dot producted V cross W, right, what we're going to find is that V cross W, if you do the determinant of that thing, we're essentially doing 1I cross producted with 2J, which is going to be 2 times the vector K, if you do that computation out. Now the vector A is 4 times the vector K, dot producted 2 times the vector K, which is going to be 8, K dotted with K, but K dotted with K is 0, 0, 1 dotted with 0, 0, 1, which is equal to 1. So there we get our number 8, which looks an awful lot like just taking the numbers 4, 1, and then 2. So you have a vector of length 4, a vector of length 1, and a vector of length 2, and you made a box, right? Now this is going it's a sketch. You see what I'm saying. But this is a perfect box. It's not wonky or lopsided because of the nature of the vectors A, V, and W. So we can say that the volume of this box is equal to 8. Not 80. Sorry about that. 8. All right. So there we have our interpretations of the dot and the cross product when it comes to area and volume.